So this is an update on last week, which was the August 28th. Now I corrected the date to last week, so I'm 1 week behind there. Um, so what we did was review minimization of functions. So you can think of it as a Taylor expansion. You truncate it to the second order case. You want to find the bottom, so you set the derivative to 0 and then solve, and you can see you're going to get this step size from that. And so here is the answer. So this is your basic Newton step. And if it's a quadratic, then you go once and you're there. So it minimizes the parabola immediately. And so you can think of that as the gradient divided by the Hessian. But because we're in one dimension, it's just one derivative. It's the first derivative divided by the second derivative. And that is your step size from your initial point, x0, which can be anywhere on the parabola. And it'll calculate the h you need to jump to the bottom of the bowl. And so that's what it's all based on. I didn't have this last time, but I realized I should have. I should have had a figure of the perceptron. So I believe this is ChatGPT's techies figure for that, and I tweaked it a bit. So you have your input, and so we've collected that into a vector. So this is either your input or it's the embeddings, it's the features from the previous layer. And then you have your weights. These are your neuron weights, and we collect those into a vector W, and we call it W hat because we're estimating those. Those are the estimates. Hats mean estimate. And then all these neurons feed into all these weights feed into a neuron, and so the output of the neuron is first an inner product of the weights with the input, and then we add a bias, which effectively allows us to set a threshold anywhere we want. And so this is just kind of a typical formulation where they have a bias input of 1, and then the bias can change that. So you learn B to change 1 into whatever bias you actually want. And so this is the computation going into this next stage. And that's what we were calling the margin. So the margin you can think of is, well, it's defined as how correct you are when you're correct. And but otherwise it's just pre-activation. It's the pre-activation dot product plus bias. And so then you go into your activation function, which they didn't really think of it that way in the perceptron days. It was really just taking the sign, but maybe it's the same thing, but it is the same thing ultimately. And so this is the activation function. It's the step size. And so this is not ready for backpropagation, right? Because the derivative of this is 0 everywhere except at 0 where it's infinity, right? So this is a highly non-differentiable function, and when you do differentiate it, you get no information. So this is what held back machine learning for quite a long time, the perceptron. So somebody had to realize, and somebody did realize, that if you make this smooth like tanh, then you can differentiate it, and then you can just keep going. You can do nested, and MLPs did come up before backpropagation. So the idea of stacking these things came very early, just a few years after the perceptron. They started stacking them up. So the multi-layer perceptron was very early, 60s. And then the backpropagation was like a couple of decades later when they did. I think they went to soft activations before the idea of backpropagation, but I'm not 100% sure about that. The history on that seems kind of murky. But in this case, we're just doing the perceptron, and it's kind of a modern view of it. And this is the final output. It's plus or minus 1. All these inputs are plus or minus 1. And it's basically a classifier. And so if it's right, then we're happy and we don't change the weights. If it's wrong, then we change the weights by the perceptron update. And so we talked a lot about that last time. And here it is. So if it's wrong, then you take the output, which is plus or minus 1, times the input vector, a vector of plus and minus 1, and you add it. And you do the same thing for the bias. And you can just think of that as all being in the weight vector if you want. And so I did a little more drilling on this. I wanted to get the times and stuff. So this is from 1958. It was motivated by a neurophysiological synaptic strengthening weakening rule. It wasn't thought of as optimization, according to what I found. All right, but now yes.
Julius, was there a learning rate or strength?
No, that's kind of interesting.
No.
Or you could say that it's 1. I mean, it depends on how you interpret it.
Yeah.
So now we're going to interpret it as a modern optimization, and
Hmm.
then effectively there is a learning rate. And it depends on what norm you say you're minimizing, whether the learning rate is one or one half or something else.
Okay.
But it's something fixed and there's no schedule. You just keep piling these things up. But of course, once it classifies everything, then it stops updating, right? So that's your convergence. So if it finally converges, and we have a guarantee that it will, if the data points are linearly separable, then it just stops, and you don't need a schedule. You don't need to fade out the learning rate.
Hmm.
Okay, so now we have any questions about that? Because now we're going to interpret it. This is back in the 50s, the way to think about it in 60s. And so it's a simple little update motivated by actual neurons. We're strengthening the neuron recognition of this data because it got it wrong. So this is for misclassification. So this pattern, we got it wrong. Let's update the weight so that it responds more strongly to that. And we also add into the bias, so that'll elevate the bias in the same direction. And that makes sense if you think of this as one big vector.
So, Julian, Julius, are you talking about it? When you say neuron, are you talking physical neuron?
Yes, actual,
Okay.
yeah.
The ones we got, I got like three of them up here, but that's about it. But I mean, those things I have in my head, huh?
Those things we still have more than the average LLM so far. As far as we
Okay.
know, we
I
don't know
feel
what's in the
better.
back room. Stutzkever probably has one that's bigger than a human head, but we'll find out. Yeah. So it just strengthens the connection. If the neurons, neurons are very random and numerous when you're born, and then as the sensory impulses come in and useful circuits get found, then those neurons get strengthened, and the ones that ultimately are not used, they literally become dead neurons, and so you lose a lot of neurons as you grow up
Hmm.
because they just never got used. Cortex gets recruited. If you have a broken sensor, then it just doesn't get any cortex, and that's why missing a sense from birth is really hard to do much about. You kind of want to cross it over into another sense. Recruit cortex from the other. So the visual cortex will reach out and take over the audio cortex and stuff like that. So it's an interesting development, and so this was directly inspired by biology. It's very very interesting and ultimately very effective, and maybe why they think like us to the surprising degree that they do. In other words, when you talk to these LLMs, you think, wow, that's a very similar brain in some way.
Hmm.
When they
Yeah.
start passing the Turing test, you start thinking, well, maybe that's how simple I am. Maybe I am just this big LLM thing. At least in the neocortex, right? We have this old brain as well, but in the limbic system, they don't, thank goodness they don't have a limbic system. I hope we never give them one. Uh, I think most of us try to stay in our neocortex and that's all they have. And so the world would be a better place if that happens, in my opinion. Okay, so we got to this update rule and interpreting now as a optimization, so you can rewrite the update rule as maximizing this. So it's a maximum of 0 and minus the output times the pre-activation margin component. So that you can also write as ReLU of minus margin. And here it is. And so now you can differentiate it. Okay, so this is now differentiable. And and so then we can apply gradient descent, and uh, and that's what we talked about last time. Okay, so we've got labels, we've got data, and we now take a gradient, and the gradient is either the perceptron update quantity, the output plus or minus one times the input vector, and negated because we want to go in the direction of the negative gradient. Well, this is the gradient, and then we will throw away that minus sign to make it the negative gradient. And if it's correctly classified, the gradient is 0 because we're over here in the max function. So now we just do the usual thing. The weight at time t plus 1 is the previous weight minus our learning interval, our learning rate, eta, times the gradient, which we just calculated. And so you write that in, and it only is active when misclassified, and you leave it alone when it's correct. So this is now our gradient descent. The minus sign is gone. We've got a learning rate now, and you can see that we're going to have to set that to 1 to get the update rule from the perceptron. Okay, so that falls out, and there's a convergence theorem from 1962, but it requires linear separability, and that's not always the case, which is why Marvin Minsky got on their case. You know, they came up with the paper introducing the XOR problem. You can't do XOR with this perceptron, just not general enough. And so, you know, there were other arguments as well, but that's one. And so the learning rate is typically 1. It's, no need for tuning because it's just going to converge to linear separation and stop. And if it can't, if it's not linearly separable, then it's just going to go forever. I don't actually know what happens. It probably gets into an orbit, probably oscillates. Um, but it could, you know, you can also imagine it going to infinity because you're just adding stuff up. So then we have a geometric interpretation. We mentioned this last time that you can think of it as pushing the decision boundary to correct classification in the space. And so I got interested. So this is what next we went straight to Newton's method, but I had to insert a quick slide on the XOR problem because I was curious about that. I wanted to know what is the minimum neural network for solving the XOR problem. And basically you need 2 layers, or you need 2 units. You need a hidden layer. So so this is the answer. And I don't see any reason we need to dwell on this, but you know, if you're watching the recording, you can pause and you can also just we can talk about it. But anyway, that's the bottom line. You just need this sort of 2-level thing where you first you have a layer that takes the sum minus a half and then the sum plus or so minus 1.5. Those implement or and respectively. And then you need the next layer to compute you know the or minus the and minus 0.5, and that'll give you XOR. Okay, so there's just no way to do that in one nonlinear operation. You need 2 successive nonlinear operations, which is very interesting. Okay, so this is what we did last time. We went straight to multivariate Taylor series. So we're just generalizing that one-dimensional story where you have a scalar function of a vector, and so this is our input. Actually, now this should actually be W. I should have written this as W. This is general math, right? So it'd be better if I wrote this as W because that's what we're really going to be doing. And F is going to be the loss function. So we want we've got some weight vector. We want to add a step vector to minimize the loss. And so let's do a quadratic expansion of the loss in you know in dimensions. That's the weight space, and so that is a quadratic approximation, and then the step size will get us to the bottom of that bowl, and so that's what we talked about. And so because we have this second order term here, we need the Hessian. So the first order approximation is just the loss function plus the step dotted with the gradient computed at where you are. So it's the local slope, but we also need the local curvature, I will say. And this is the curvature in the direction h. So the Hessian is the matrix of second derivatives. And so if you dot it on both sides with the step that you want to take, the the quadratic form, then that gives you the curvature. And so here's the full matrix. All right, so and you can also write the Hessian as the Jacobian of the gradient. We talked about that. And so now we generalize Newton's method to this case. And so before we had that the step size was the derivative divided by the second derivative, but now it becomes the gradient pre-multiplied by the inverse Hessian, the inverse matrix of second derivatives. So it's exactly analogous, just generalized to n dimensions. And so that's Newton's method in any number of dimensions. And so we're minimizing in one step the local parabolic approximation to the loss function, the loss surface, the loss landscape, people like to say. So now this is new, and it's based on Ted's remark. We had some discussion about the decomposition, the orthogonality, the rotation, all that good stuff. So here's just kind of a wrap up of the properties of the Hessian. It's a matrix of second derivatives, and so it's going to be positive semi-definite, in a paraboloid because there are no saddle points. Okay, there's no everything. The curvature is all pointing in the same direction. That's that kind of thing, and so it's. And we're going to approximate it as a sum of outer products of gradients, and that will guarantee that even in practice, it will be positive semi-definite. Okay. And that has a really good advantage of not letting you go in the wrong direction. You don't want to flip the sign of the gradient and go the wrong way. Okay. So any symmetric matrix has real eigenvalues, and a positive semi-definite matrix has them all 0 or positive, and the eigenvectors are all orthogonal, and that's a really important, valuable thing. And we really needed that for our discussion because that's why you only get ellipsoids at some orientation. Um, if they were not orthogonal eigenvectors, then you might have a distorted ellipse where the major and minor axis are not orthogonal, but they are. So we don't have to worry about that. And another property of this, because it's symmetric, is that its SVD reduces, you don't even need an SVD. You can just do a similarity transformation. So you basically just have an orthogonal matrix, a diagonal matrix, and the same orthogonal matrix transposed, which is the same as its inverse. So, so that's the really simple form that you have. And so this Q matrix is your matrix of eigenvectors. They're all orthogonal, and we normally take unit norm. You can choose any norm. So you just have this orthonormal matrix, and then this diagonal will contain all your eigenvalues, which will be your curvatures along the coordinate axes. And so then H inverse is very simple. So when you invert this, remember that you string it around backwards, and QT inverse is just Q, and Q inverse is QT. And so you get this. So inverting the matrix basically just means invert the diagonal all by itself. And so for that, we need positive definite. And so if it's got a 0 in the diagonal, then you add epsilon. And that's got a name. It's Levenberg-Marquardt, you probably have heard of. And so in practice, we always add a little epsilon to the diagonal so that you can't divide by 0 accidentally. And you can also think of it as going between Newton's step and gradient step. So it sort of reduces back to Newton's method with some arbitrary step size when you don't have an eigenvalue at that particular location. It's basically a dimension that has no information. There's just no data coming in to tell you which way to go. And so you're just picking some arbitrary step size corresponding to for the gradient. All right, so this is now easy to intuit. So we have the Newton step can now be broken down into, you take your gradient, you rotate it. An orthogonal matrix is a rigid rotation in Rn, and that's going to be this ellipsoidal thing. And so you've rotated it so that the major and minor ellipses of the ellipsoids, axes of the ellipsoids are coordinate aligned. And now you can apply this diagonal matrix to normalize each curvature. So each curvature gets divided. So each coordinate gets divided by the curvature so that it becomes unit curvature. That makes it into a circle. So this aligns the ellipsoids to the coordinate. It rotates the ellipsoid to coordinate alignment. This normalizes the ellipsoid to make it a hypersphere. And then this just goes back to we got to go back to the coordinates we came from, right? Because we're stepping in those coordinates. Another nice thing to do would be to constantly orthogonalize, or let's say rotate your whole problem into, the orthogonal space where the ellipsoids are aligned. But that's changing all the time. But it's an interesting direction to pursue, and I'm sure it's been pursued by now, I'm sure. All right, so then that's our step size, okay? So you got a gradient, you rotate it to align the axes of the ellipsoids, and then you normalize curvature, and then you come back to your space. There's your Newton step. So it's carrying this out. And I made a graphic. I think it was ChatGPT 5 who wrote this. This is a techies figure, and it's pretty nice. So here's your original hyperellipsoid, and your major and minor axis is not coordinate aligned. So you go through the orthogonal matrix that rotates it so that let's say this is the gradient with respect to E1 coordinate, let's say eigenvector 1. So this is the major principal axis of the ellipsoid, and we're just going to track that one. And so after rotation, it shows up here on the first coordinate. And then now we multiply by minus d inverse. That's going to normalize it. It's also going to flip the sign because the step wants to be in the negative gradient direction. So let's just stick that there. Then we can use h as our notation. And the tilde denotes that we're in the rotated space. So we have gradient tilde, nabla tilde here, and we have h tilde here because we're in the rotated coordinates. But now this ellipse has been normalized to a hypersphere, or a circle in this case. And so now we go back to the original space and we get our step size h. So the h in the E1 component is here. And so then you can look at that for every component. We could do it for the minor axis here and for all the axes you have. So that's the discussion that was what Ted brought up that I thought would really be nice to illustrate. Any questions or discussion about that? Cool. Well, so
Roger, did you have a question?
Yeah, sorry, I was on mute. I was just wondering from the visual notation on the top versus the equation in step 2. Is there an inversion? Is the minus sign reflected in the visualization?
just in the change of notation. So so by labeling this as minus,
Oh, okay, over there. Yep,
yeah,
gotcha.
and
Gotcha.
there's a minus sign here too. So a little bit of sleight of hand there, but I just wanted to not introduce new notation. I'm just trying to stick with the symbols I have, and
Okay,
yeah. So yeah, it's a little bit of a fudge there, just to keep it down to gradient and step size, and yeah.
okay.
So but yeah, you could argue that maybe this should be going over here, right? Why don't I just point that way? That would make it a little more intuitive. Yeah, I should do that. Yeah, I easily fix this in the TXI by changing this arrowhead to a minus in this location.
Okay.
So yeah, and this should come out pointing that way. It's been reflected. All right.
So
Yeah.
Julius, just a quick comment on this slide. So what you're showing is the component of the gradient E1.
Yeah.
Okay. And if you did this with all the individual components, what you could do, so imagine the second component would be perpendicular to this one, so it'd be pointing kind of northwest, right?
Mhm.
Right. So if you did all those individually and then you sort of restored your original gradient, you can imagine that you could do the same thing all in one fell swoop. So let's say we had a purple vector pointing due north on the left in your diagram 0. Okay, so it's not E1 or E2, it's a little mix of them. Then when you rotate it, right, it's still pointing, now it's kind of pointing northeast, right? You're going to do the shrinking and it's still going to be on the perimeter of the circle. It'll have been shrunk simultaneously in the X and the Y directions, but different amounts based on our D inverse. And then we're going to rotate it back and you'll see once again it'll be pointing due north again. So you don't have to do this one coordinate at a time. Julius was just showing us one coordinate because it's a little bit easier to think about a single coordinate because it's like a basis vector. But the reality is you can do all of the different coordinates simultaneously. So I thought I would just comment on that.
Yeah. It's from ellipsoid to hypersphere, and but it does need to rotate because it's only got this diagonal to apply. Or if you don't rotate, of course, you can just invert this giant matrix, right? So so if you have the whole matrix in an inverse form, then you just multiply the gradient by that matrix. But we normally don't have that. There is one case where you do, though. The recursive Gauss-Newton method maintains a recursive update of H inverse, or the approximation of it. And that is what it keeps around. And so it does multiply the gradient by the current estimated inverse Hessian. That's something that has influenced later algorithms as well. I have a slide on that.
And the dimensions on the Hessian are the number of parameters squared. Is that correct? Number of parameters by number of parameters
Hmm.
square matrix?
Yes,
Okay. Okay.
it's big.
Pretty unwieldy for deep learning.
That's right. Yeah, the great thing about deep learning is that everything is scaled to such a size that you have to use the simplest algorithms. It's the bitter lesson. The bitter lesson is actually a real boon to people who don't really want to have to, think hard about, exotic algorithms. At scale, it just seems like the simplest stuff wins. But what's really hard work is testing them all out, doing all the ablation studies. I mean, it's enormous work, right? But it's more experimental science than theoretical science. Well, it's experiment guided by theory, and that's why we want to understand it, right? Because our theoretical understandings will guide new studies. We'll try new things and maybe try you know, the right things. There's so many things you could try, right? Okay, so then we had some graphics that we talked about. This is just visualizing the same stuff. And and here's where we got wrapped around the axle. It was kind of fun. So we were doing a Newton step for the perceptron squared error. Okay, so our loss function we defined as the squared perceptron. So we've squared the margin here, and you put the 1/2 in there just so that when you differentiate, it goes away. So here's now the gradient, and it looks like the ordinary perceptron step, except that this is the error, so it would actually be 0 or 2 as opposed to 0 or 1. So that's where you can then now say that the corresponding learning rate is 1/2 to cancel that factor of 2. And so and so so I'm sorry I mentioned Claude. It was actually ChatGPT that tried to invert this, and I didn't catch it, but Roger caught it. And so the Hessian, which is an exact calculation, you differentiate the gradient with respect to W, and you get x transpose, and here it is. And so we just brainstormed it and decided, well, we can't invert the Hessian, but let's just use its trace because the trace is the sum of the eigenvalues. And what you really want to do is just divide all the coordinates in the rotated space by the eigenvalue for each coordinate. So we only have one eigenvalue here. This is a rank 1 matrix. So the sum of eigenvalues is the eigenvalue, right? So that's really nice. And so it's elegant. And so we put that in there, and lo and behold, we get the same answer that ChatGPT just kind of wrote down, because that is what it becomes when it becomes full rank. So if you go on and if you add a bunch of these together, then it will become full rank, and you can actually do this, and then you get the same answer. But you have this different. You have to do something else when you're starting up and you don't have enough data, and you have to define your loss differently. You can't be sample by sample the way the perceptron does it. It has to be, defined over time as a sum of errors. So we'd have to add these up to get full rank. Okay, so there it is. The Newton's method on squared error gives a perceptron update for unit norm input. So if you take a unit norm input or normalize, you just do RMS norm first thing, then this goes away and you get your good old perceptron update and you use a mu of 1/2 to really get it. So that's really fun. Okay, so that was nice. And so then I went back to ChatGPT 5 and I said, all right, I just noticed we have a problem with this matrix. It's rank 1 and we can't invert it. How do we save this derivation? And it was good. It just immediately knew what to do. It went to the Moore Penrose pseudo inverse. And so you think of that as just inverting the part of the space that you can and leaving the rest of it alone. So this is the projection operator onto x of I. And so x transpose will take a dot product with whatever you give it, and that'll project it into that's the projection coefficient, and then you multiply that by x itself, and that's your projection. This is the normalization needed in projection. And so this is the projection operator. It'll take any vector, you multiply by any vector, and you get the component of that vector along x of I. And then the Moore Penrose pseudo inverse is got this plus notation here, and so you've got the projection operator, and um, and you divide by the norm squared. I wonder if that's in there twice. I have to look at that again. So then here's the answer. The step in the weights is minus the pseudo inverse times the gradient, and that's very elegant, very reasonable looking. And so you write that down, and yeah, this is not here because that would give it again here. So yeah, I'm going to erase that in my next correction. And so then that's the answer, and you get the same answer, and that's really nice. And so then just to wrap it up, here's what I think. So these are the same equations as before. You've got your gradient, your Hessian, exact, your negative gradient. You want minus H inverse delta, but you can't invert this. So you just look at this for a moment and you realize, well, look, the step size has to be in the direction of the gradient because anything else is going to be annihilated because the Hessian is an unnormalized projection operation onto x sub I. So might as well just choose your step to be some alpha times x sub I. So you might as well just say some multiple of x will be our step. And then let's see if we can solve for it. And so you plug that in and it's soluble and you get the same answer. And to me, that's the most direct way to see it and get the same answer. And you don't have to think about the pseudo inverse in some, fancy textbook formulation. It's just direct bottom up derivation. Okay, so then that's how far. And so now we're done with last week and we're moving forward. So my next topic was Gauss-Newton and then stochastic approximation and then muon. And I can turn the floor over to anyone else. So we're doing pretty well on time. All right, so Gauss-Newton. So here you have a least squares formulation once again. So it's very common to do sum of squares in this sort of domain. This is, again, my background is system identification. I would say I have half a PhD in system identification, the other half being on filter design. I sort of pivoted away from this because it's very much online, real time, and I wanted to get into, global optimal stuff. And so I studied this stuff really hard for about 2 years, and least squares was the king. So there's your loss function. It's a sum of squared errors over all time, finite time, over the whole data set. And now you take the gradient and you get this, okay? And so the chain rule makes so what's maybe a little bit so what's new here is that our gradient will be multiplied by the error because of the squaring, okay? And you need that because now when you take the Hessian you get, by the chain rule, you'll get the gradient times its transpose, and the other term will be the error times the second derivative. And so we want to assume that the error is small so that we can get rid of this term. And that allows us to approximate the Hessian near the solution, let's say, with the sum of outer products of the gradient. Okay, so that's the basic idea behind Gauss-Newton. And then in practice, you just update this recursively. And it's very similar to shampoo. If you look at this, I just looked at the shampoo paper right before today because Roger and I were talking about it on Slack, and it's very similar. Okay, so Gauss-Newton, neglect second order derivatives, approximate the Hessian as the sum of outer products. It will be positive semi-definite, but we always add an epsilon to make it positive definite, make sure that it's invertible. And you can't get into a problem with saddle points or anything like that because this is, sum of outer products. It can only build a positive semi-definite matrix. And so adding epsilon normally brings in the name Levenberg-Marquardt. I've also seen it called damped least squares. And as I was saying before, when your second derivative vanishes and you start relying on this, it reduces to gradient descent with step size 1 over epsilon times whatever your outer step size is. And so it looks similar to shampoo. And I think we'll probably be talking about that a little bit later. Okay. So now Here's the one that I was using all the time. It was definitely the front runner. It was like the main system identification algorithm in the 80s, let's say. It's the recursive Gauss-Newton least squares algorithm. So your parameter vector, in our case, the weight vector, gets updated by this, running summary of the inverse Hessian times the gradient of the error, which is the error times the gradient. Well, it's the gradient of the error squared, which is, which is this, all right, as we talked about. And so there's this update rule. So you update it. You can think of the Hessian update as being like this. It's just like the momentum calculations. You can think of it as, outer product momentum. And so you have a forgetting factor lambda. It's often called, what are they called? Learning rates. Like in Atom Optimizer, those two parameters you said, the beta and the alpha. That's what this is, right? And so you're scaling it by 0.95 or whatever, and then adding in the new one. And sometimes you'll see 1 minus lambda sub n here, and that gives you a kind of normalization, so that if it were constant, it would converge to the right thing. And so that's the Hessian update, and then the inverse Hessian requires a fast algorithm that works for rank one update. So this is a rank one update, and there's this thing called the Woodbury matrix identity that you can look up on Wikipedia or wherever to get the details of it. So there's a very efficient update to the inverse when your update is rank one. And so that's what everybody used. And it's still expensive at scale, but it does do a full Newton's method. And you don't ever invert the whole matrix. You're sort of going along, updating your inverse with rank one updates.
What's the dimensions on the R?
R is parameter space by parameter space. So it's weight length,
Still.
weight length. So it's your full covariance matrix.
Okay.
Yeah, number of weights total. So then the question becomes, what can we do that's in between? Because this is something we talked about, that if you've got a billion parameters in your model, then your Hessian and your inverse Hessian have 10 to the 18 parameters. You don't even want to store that in memory anywhere, right? It's just too much. I mean, you only need half of it because it's symmetric, but still, it's really big. So what can we do in between Newton's method and gradient descent that does not square the number of parameters? And so that's the name of the game in a lot of these exotic methods that end up being simple at scale. So the stochastic approximation method is the one that existed in the 1980s for, getting rid of the quadratic dependency. And in that one, you just approximate the Hessian by its diagonal. So you get rid of the rotation step. And it's like Ted was saying, if you don't rotate, you just multiply by the matrix. It'll act on both of them. It'll act on all the coordinates together. So it'll be a kind of a compromise thing. Then you have a higher burden of data normalization. So if you've normalized your data such that all the dimensions are just spontaneously normalized, then this should work really well, right? So you don't have the ability anymore to compensate for vastly different curvatures. And just one intuition for curvature is that you can think of it as amount of information. If you have no information, the curvature is zero. It's flat, and you have no information, and you can't invert the Hessian. If you have a very high curvature, then you get a lot of information from the lost landscape, and you want to set a very small step size and go down into that narrow valley. And then in the worst case is where you have a very narrow valley and a very broad valley on the next dimension, because there's no step size that's good for both of them. You're either going very, very slow along the broad valley, or you're stitching back and forth in the very sharp valley, and you might even go flying out of it. So it's very ill-conditioned. And in matrix numerical linear algebra, that's a very precise term. Ill-conditioned is the ratio of the maximum eigenvalue over the minimum eigenvalue. That's your condition number, if I don't have that backwards. And so you can see that a well-normalized space will have a condition number of 1. All the eigenvalues will just spontaneously be the same, and the curvature is the same. It's already, a hypersphere, not a hyperellipsoid, especially not a long, skinny hyperellipsoid. And so you can do this in that case, and you're just looking for that common curvature. And to the extent that the curvatures are comparable, this approximation should work okay. Okay, so that's then the idea of the stochastic approximation. The covariance matrix is updated by, forgetting the previous one a little bit and adding in the diagonal of the outer product of the gradient. And this should have a transpose on it. And this means pointwise multiplication. Oh, I guess pointwise multiplication doesn't need the
Right.
transpose. Yeah.
So, Julius, at the risk of stating the obvious, we can normalize our inputs to a neural network, but once we have a deep neural network, then we no longer know whether intermediate values are all going to be well normalized, and so that poses a challenge.
Absolutely. But we see, in the history of deep learning, a lot of progress has been made by adding normalization that we have added, right? Like RMS norm was a big step forward, right? And I think you can interpret the skip connection along these lines. So the more normalization, normalization has really improved things. It has, advanced the size that we can handle. And so maybe we can push it in this direction. Maybe there's a way to extend normalization to normalizing across dimensions of the curvature, across the dimensions of the model space and the eigenspace. And I'm sure people have worked on that. I'm sure there are papers out there, but it's multidimensional normalization, not just RMS norm, not just layer norm. So yeah,
Yeah,
but
I,
you're
I,
right.
I unfortunately, I could be wrong, but I don't think the normalization layers that we have help us with this problem. I think mostly what they help with is just things like exploding, vanishing numbers and gradients. So we just keep our floating point numbers similar to the one-ish range when we normalize, and then the gradients will be some relationship to the magnitude of your inputs. At that
Hmm.
point,
Hmm. Yeah.
when you normalize your inputs to your model, and it doesn't matter whether it's a linear model, neural network, gradient boosting or whatever, what you'll notice is the real pattern is you transform things. So let's say you want them all to be roughly on the scale of 1, and so if you have age and you're like, oh, that's 0 to 100, so super simple, let's say I divide by 100. Okay. What you have to do at the back end is you have to multiply by 100 in order to restore it. Okay, so that's what we don't have in our normalization layers, is we don't have sort of this restoration. It's just this one-way normalization.
Hmm.
So that's why I'm thinking it doesn't really accomplish improving condition. It just manages overall scale.
Yeah, it's one
But
degree of freedom.
Ted, to your example though, isn't the output in that case it's arbitrary, it's the input to the next layer. So you don't really need to invert that initial divide by 100.
Good point. It'll go away. If you have a next layer, the RMS norm of the next layer is going to just take care of anything at once.
Yeah, until you get to maybe that final, output projection.
Yeah, the final out, some linear connection at the end, yeah, can come out unnormalized. But then softmax is going to normalize.
Right.
Well,
I'm
what
not sure. Yeah, I haven't thought about this. Maybe the issue then is when you have your, I don't know what you want to call it, your peers in your layer. Um, you you want just like in your XOR very simple problem, the magnitude of one of those is sort of bigger than the other, and you kind of want that property. And if you just took the output of every single neuron and squashed it to be unit normal, then I think you have to be careful, because then when you recombine those in the next layer, I'm not sure if everything's still happy or if there's potentially problems.
Well, I'm pretty comfortable with one layer. And in that case, RMS norm takes care of 1 degree of freedom. But for the rest, you need to normalize the data, specifically. And we talked about this last time. That's what preemphasis is for when the data are speech samples.
Mhm, mhm.
And so it's all about knowing what your dimensions are and knowing how to precondition, how to pre-process your data so that it presents equal energy in every coordinate direction, which in the case we talked about were the frequency axes. And so that's the normalization on the data. So you can do it on the data side, so you can provide it that way. Now that's just it's not going to help you in the second layer. Right? So in the second layer, if the first layer makes a mess out of it, then all bets are off, right? But at least for the
But
first layer.
yeah, it kind of feels like you need the preconditioning for the second layer then. It's whatever the distribution is on the output of the first layer, you want to whiten that so the next layer sees a energy across all neurons.
Yeah, so there's a new invention waiting to happen. What do you do? But if it's a well-formed first layer, then it should tee up something nice for the second layer. I don't know.
Yeah.
I don't know if that works. I mean, I hope that works. I mean, it certainly works better than I expected. So maybe that's happening. But maybe we could do that. Maybe we can help it that way.
Yeah, I think with some thought you can figure out how to do it. That what was the model called NGPT or whatever, but the one where everything was on the hypersphere.
Yeah.
Everything, the weights and the outputs, I think were always well, no, that's still unit norm. That's not, it still could be ill conditioned.
And
Yeah.
the old persistent excitation intuition is it won't be ill-conditioned if you have persistent excitation in every dimension. So again, at the input to the first layer, as long as you have
Right.
the
Yeah.
same amount of energy at all frequencies, then you'll get that property that you want. And so then it becomes how to enforce that in the output for the next layer. But to solve that, you have to know what your dimensions are and where they are, and then and try to normalize them.
So as soon as you have interactions between the different dimensions, then you really can't easily normalize them. Uh, so
Yeah.
so that may be a preview to what we're about to see with Muon in terms of the rotation, because if you have an ellipse on that's on a diagonal. Well, actually, ellipse isn't so bad, but if you have a non-linear
Hmm.
relationship between your two axes, then that ellipse is now, let's say, a horseshoe, and there's just no way to guarantee that things stay nicely conditioned if your data distribution looks like a horseshoe.
How about this? What if you
Let's,
go ahead?
oh, I was just going to say, I was going to suggest we come back to this because Ted, you might be right. Muon might be addressing that issue.
Yeah, I mean, not perfectly, but try taking a step in that direction. Yeah.
Yeah, let's get to Muon and come back to this. But just the one thing I wanted to say though is that extending this principle of persistent excitation from the first layer to subsequent layers, it is possible to throw a projection back. So for every layer, you can measure the orthogonality of the dimensions, and so you could then imagine optimizing your input data to give you equal variance on average in all dimensions across all layers. That might be an
But only on average.
right.
So if your data looks like a horseshoe, you can have variance one, but for any given data, it can be very ill conditioned. if
Right.
it's a super skinny horseshoe.
Yes. But we can use momentum. So let's
All
talk
right,
about
let's keep
momentum.
going. Yeah.
And that's the next topic. So what a perfect segue. So the atom optimizer. So extensively used, and it basically uses the average gradient instead of the instantaneous gradient. It's the average gradient, and that's what the momentum. And it's an exponential moving average. So that's the nature of the averaging, and it's called momentum. And that's an intuitive. I think that's a good intuitive term for it. So if the gradient vanishes on a particular step, you're okay because you'll just effectively use the previous gradient. Okay, and in case of atom, you not only have momentum for the gradient, you also have it for the squared gradient, and you keep them both going. And so here they are. So the gradient average is, EMA means exponential moving average, and you feed it the gradient. And here's the actual formula for it. So you've got a forgetting factor beta 1, and then you have 1 minus that for the input scaling. And as I was saying, if the gradient goes constant, then this will be unbiased. It will go straight to, it'll converge. So when these are equal, you can see that you add up to just get the gradient. Okay, it settles down. I actually just think of it as a low pass filter that's got unity DC gain. We use these all the time in audio. And then the same thing for the squared gradient. And this is, component-wise squared gradient that's being exponentially moving averaged. And so you can just call that the second moment, exponentially averaged second moment. And so that's and that's it's interesting because the first thing to come along was the momentum for the gradient, and then the second thing to come along was this exponential moving average of the second moments that then divided, that normalized the gradient. But they that was Hinton, and Hinton didn't have um, the momentum on the gradient. But then the people who combined them together, that was Adam. So, and I have a little timeline on that. I thought it was interesting that it came in 3 steps. And so then this is your update. So your weight is updated by the gradient divided by an epsilon in case it's 0, plus the square root of the element by element squared gradient. So this is an update for the ith element of the weight at time t. So this is only one weight at a time because this normalization is different for every weight component. So each weight component is individually normalized so that the gradient um, is that component of the gradient divided by the you can think of it as the RMS level of that gradient. So RMS normalized gradient components with divide by 0 protection. So that's Atom, and we're using it all day. We all use it, right? It's everywhere. So alpha is your learning rate. Everybody's played with that. And epsilon guards against divide by 0. And this dividing out by where's the division by? I don't see that. That's something that at startup you actually can divide by this because if you don't have in the first several steps, you don't want to you have a bias. In other words, let's say it's
Or low
constant,
pass or
but
low pass filter lag, right?
yeah, it's the low pass filter rise. It's the rise time of the low pass filter. So you're dividing out the rise time envelope of the low pass
Right.
filter.
Hmm.
And that's really valuable for it gives you an unbiased estimate for every step without having that transient in there. And then and if you want AMS grad, then you just make this little change here where you replace this with this, and it just has a little more memory. So you take the max of the second moment for the current time and the previous time, and it's like giving you a little more memory, a little more history. And here's a history diagram that GPT-5 did for me. So we started with stochastic gradient descent. That's very, very old. And then momentum was added to that in 1964 by Polyak. And then RMS prop was independently added to stochastic gradient descent by Hinton in 2012, so much later. And then finally, Kingma and Ba added, combined them, momentum and RMS prop were combined, and also the bias correction came in then, and that was 3 years after RMS prop, which was only the RMS scaling of the gradient, and then here's AMS grad a bit later. So that's a little bit of history, and so here's kind of a wrap up on Muon.
So
So
before we go to Muon,
yeah,
do, do people have a good intuition for Adam? I feel like I have a slightly better intuition based on your explanation, Julius, but I don't know if it would be helpful to give kind of a geometric interpretation to it.
sure, yeah. Well, you're normalizing the gradient element wise to
Yeah.
the average to have a unit norm on average.
Yeah, so basically what I'm thinking is if you've ever seen um uh this skinny valley, kind of depicted. I could probably do Google search and find one. But if you took a piece of paper and you folded it to a very sharp V, okay, then all the gradients at any point other than on the actual valley floor at the fold, all the gradients point directly towards the fold. But if
Mhm.
your V is tilted slightly, okay, then when you're on the valley floor, there is definitely a downhill direction. But the problem with vanilla SGD is that all the gradients are basically pointing perpendicular, more or less, to the actual downhill direction of the valley floor. They're always pointing, down the steep sides towards the valley.
Mhm.
And so if you've seen the diagrams, then SGD, vanilla SGD will zigzag, okay, from one side to the other, unless you happen to nail the learning rate just right so that you get lucky enough to be really at the bottom. But anywhere other than the bottom, the gradients are pointing perpendicular. So the cool thing is when you add momentum, if you imagine zigzagging, you've got one that's going a little bit forward, but mostly to the left, and the next one's going a little bit forward, but mostly to the right. When you combine those, they tend to cancel out, and so what you get left with is just the forwards.
Nice.
Okay.
Am I
Um,
But
correctly?
is that's just the momentum, isn't it?
that's just the momentum, okay? So
Right,
the
right.
momentum gets you going in the right direction. But the problem with just getting you in the right direction is it still doesn't fix the learning rate.
Mhm.
So if your gradients are pointing towards the valley floor, and if your valley is steep enough, okay, then let's say the magnitude in the down towards the floor is 1,000, and the magnitude of the slope going down the bottom of the valley is a 1. You'll get these thousands and negative thousands to cancel each other out when you use momentum, but you're still only moving one at a time along the valley floor. And what you'd like to do is to be able to move a little bit faster, okay?
Mhm.
So I think the geometric intuition I have is that when you then square the the gradient components, okay? And so on the valley floor direction, you have 1, 1, 1, 1, 1, 1, 1, 1, 1, okay? But in the side direction, you have positive 1,000, negative 1,000, positive 1,000, negative 1,000. The variance is very, very large in in that direction. And so what that can then tell you is that the curvature in that direction is way higher, whereas the curvature in the floor is way lower. And since we're dividing by that, that's what then allows you to scale to make the steep curvature of the valley suddenly look a lot flatter so that you're now resembling more our circular bowl.
Am
Yeah.
I
Okay.
Ted, I'm wondering, is the intuition that the squared term is basically telling me that my step size is too large in that direction, that I'm overshooting the optimum?
Well, and a
Uh,
very clean way to think of it is it normalizes the gradient in each component so that the learning rate is the same in
Yeah,
every
yeah.
component. Yeah, it
Yeah.
normalizes the gradient so that it's even reasonable to have one learning array. If you didn't normalize it, you would argue that, well, I need separate learning rates in every dimension, and that's what the Hessian gives you, is it gives you those different step sizes in every dimension. So this is a very nice, simple way to do it, component by component. It's essentially like the stochastic approximation method, but it's using the square root it's off by a square. So if you didn't take the square root, this is normalizing it to one. If you so this is RMS. If you just left it alone as a square, then that would be the stochastic approximation.
Yeah, and I don't know how much value there is to using the square root of the squares versus if you just used the average of the absolute values or something like that.
Right,
Uh,
right. L1
but
norm. Probably
but
similar.
but so what it's going to do is it's going to take those high curvature areas and it's going to divide by a bigger number. Um, Now, theoretically, that doesn't do anything to speed you up in the valley floor direction, but if it lowers it so that it's sort of one in every direction, then obviously you're still going to do your global learning rate search, and you're going to find a certain. So if you didn't have this, then you would have to use a very tiny learning rate potentially in order to not diverge in the steep direction.
For the
But this allows you to use a larger learning rate sort of everywhere.
for the
Uh,
learning rate in the like in the sort of like geometric mental model here, is the learning rate if there's a valley floor and that's where I kind of want to be, but the rate at which I'm traveling down that floor is effectively the learning rate here? Or what's the
The step
I,
size.
it's the step size. So you want to be taking big steps, but if your steps are just going from one end of the valley, one steep side of the valley to the other steep side of the valley and back and forth, these giant steps are not actually progressing you sort of in the downhill direction that the valley is pointing.
oh, because you're kind of stepping in onto this like slope kind of side thing and just going back and forth in that way, kind of.
Because when you have a sharp V, I don't know if you can see my
I
hands,
get,
but
yeah.
but the gradient is pointing downhill towards the valley. The direction you want to ultimately be moving is down the valley floor, and that's roughly perpendicular to the gradient.
Mm-hmm. Okay. Okay.
Okay,
Got it. I think.
so momentum
And
will help you out, but it still doesn't help with your conditioning. If you then divide the valley by a large number, now all of a sudden you get something that's more like a circular flat bowl. In this case, it's still a valley, but
Mhm.
now you can use a similar learning rate in both directions.
Hmm.
yeah,
Okay.
yeah.
Now the
I was
thing
going to
that I
say
don't
that.
remember is, does Atom break down? I think Atom breaks down as soon as your valley is no longer coordinate aligned if it's diagonal. Okay. And then the next hairier thing is if your valley is no longer straight like a piece of paper folded, but it's curved. Okay. But I think with Atom, uh, as soon as your valley's at a 45-degree angle, you're a little bit up the creek.
Which it's
Hmm.
always going to be at an angle.
That's the problem, is
Yeah.
that the odds of it being super close to aligned are not great. And so thus everyone's searching for the next best thing, and then Julius, I think you were gonna then transition to Muon.
Hmm.
So because the scale of the dimensions is different, can be different, um, when I have a small gradient, means it's not very steep. That could either be that I'm in a high curvature area at the bottom, or I'm in a low curvature area and I have a long ways to go, right? So the step size is difficult in that context. In Atom, it looks like Atom is using an RMS norm of the loss, but it's not actually a second order. It's not measuring curvature, right?
It's using gradients from separate, we'll call it mini batches, because that's what we normally do. It's using the distribution of gradients from the mini batches to try to guess at the curvature. Okay? If you get
Oh, so it's kind of
if you
sampling the gradient at every
yeah,
point,
at each time
and
step, at each batch optimizer step. And if you're getting very consistent gradients, that's good news. But if you're getting very inconsistent gradients, that would imply that you might have high curvature in that dimension.
Yeah, what I have here on mine is the exponential moving average in Atom can cause it to forget rare but highly informative gradients too quickly. Is that kind of the problem we're discussing there?
Well, we're not talking about the problem. We're actually talking
yeah,
about what Atom is good at
Okay.
first.
yeah.
So, and so even simpler than the valley problem. Let's say you just have a flat surface, but it's tilted so that it's 1,000, you know, whatever the units are
Mhm.
in the x direction, but only 1 unit in the y direction. Right? You really just want to be taking bigger steps in the y direction and smaller steps in the x direction.
Okay.
And Adam's good at that, right?
And Atom will do that for you.
Yeah, yeah.
And then Atom will also work a little bit in valleys because the square means it doesn't have to be flat. The square will always be a positive number. And so if you have alternating positive and negative numbers, then it still also works.
Hmm. Gotcha.
So that's the goal, is to use that over time, that EMA in each component direction to guesstimate the curvature. But the curvature it's guesstimating is a diagonal Hessian because it's
Right.
only doing each coordinate.
Independently, yeah.
Yep. And that's, I believe, where Muon can be stronger.
And so that's where the you were saying the rotation becomes a problem then, because it's doing them independently.
Yeah.
Gotcha.
Yep.
All right. I only have a couple more slides. Should I go through them?
Yeah.
Sorry for the
Okay.
interruption.
Oh, no, that's great. That's real content. Can you see my my presentation again?
We can.
Yep.
Okay. And by the way, I found another thing that I wanted to show you. This is a diagram from a thesis that I like. It's a thesis by Max Kamenetsky. I think he was Widrow's last student, and he has some really great discussion of all these algorithms and in the geometry of dealing with the curvature, and writes it all up really well. So anyway, that's a nice resource.
Can you
Uh,
post a link to that?
Actually, it's a PDF. I'll see if I can find the link and then post that.
Okay.
Where is my? Oh, I know what I have to. I think I have to go to another screen. Okay. So here we are. Muon. Another thing, I think you probably covered this, but if if it just so happens that your Hessian is aligned, so that its eigenvectors, if the eigenvectors of the Hessian are on the coordinate axes, then basically Atom is normalizing the same way a Newton step would do, except for the square root. You would not have the square root, so it is a little bit different that way. But as Ted was saying, qualitatively, you're doing the right thing. And if you're not doing least squares, then maybe that is right. So you have control over what you're doing by what norm you're really minimizing. And so L1 norm is different from L2 norm and so on. So there's a story there. So, in other words, the atom optimization is ideal the more your natural covariance eigenvectors are already orthogonal along gradient component. So if your gradient components are independent, if they're orthogonal statistically, then you get a really great result, right? And it's okay if they're correlated as long as they're comparable. So you can have circular correlations, and that's fine. You just don't want to be have one gradient component corresponding correlated with another gradient component that's very differently scaled. And so one thing I always do is I think really hard about my normalizations. I want everything to be unit variance, and everywhere you look, it's just everything's unit variance and everything's decorrelated. I even work hard to decorrelate my parameters so that I don't have correlated inputs. But as Ted was saying, you don't have control over the subsequent layers, but at least going in, you can have control. And there's the history. Here's Muon. Uh, and so, yeah, we haven't talked about Muon. Okay, so the key innovation of momentum, according to this summary, I think this is an AI summary. Yes, I normally I add that. I would say, ChatGPT 5 plus editing. So, that's an editorial mistake here. I definitely got this from ChatGPT 5. And of course, I check things when I have time, when I have to. So the key innovation is to normalize the average gradient to the hypersphere. So here it is. And what's the difference from Atom? This is no longer component wise. This is the whole gradient. So we're going to have some way to estimate the norm of the whole gradient. And as we talked about last week, that's expensive. It's an operation that goes across all the weights. So if you have your, what is it called? Weight slicing, partitioning across GPUs, then now you've got the problem of having to combine, the outputs of multiple GPUs to get those weights and form this aggregate norm that you can now feed in and normalize with. But apparently they work all that out, and it's better at scale. That's the bottom line according to my research, which is very preliminary. So you got the same kind of momentum on the gradient. They do away with that 1 minus beta scaling, so there's no concern about the early bias, I guess, because at scale you've got so much data, that's not an issue. The rise time of the low pass filter is negligible compared to everything else. And now you update your weights like this. It looks just like Atom, except that we have the norm of the gradient instead of a component-wise RM second moment square root. And so we have unit norm updates. We have no bias correction. We have no adaptive per parameter rate estimates. It's global normalization instead of element-wise normalization. You only have to track momentum, not second moments, but you have to compute the norm of the gradient. That's even worse. The second moments were just element-wise by element-wise, and those partition nicely. And so the word is that it wins at scale, and that's what people are reporting. So the design philosophy is it's stochastic gradient descent with momentum plus normalization of the overall gradient. So it's the gradient being projected to the hypersphere or scaled to the hypersphere as opposed to normalized component by component. Okay, and so you just think of it a little bit differently, and it's particularly effective for LLMs and large-scale training where the unit norm property ensures stability across different parameter groups, such as embedding, attention, and feed-forward layers. So that's the word on this. I have no direct experience here. The typical parameters here are beta 0.95 for the gradient momentum, and
I do want to raise the point on Muon in that maybe it works at a certain level of scale, but my understanding with Muon was that once you go kind of above the like 1B range, you get a lot of I think it was that your loss curve can start spiking a lot, which was one of the reasons why they used Muon clip instead of Muon like raw with Kimmy, if I recall correctly. Is that track to anybody or?
Yep, correct.
And I think that's partly just a phenomenon that LLMs have as part of the way we currently build them. They have extremely large activations, which are necessary. You can't just squash those. So
Interesting.
So you have to find a way of dealing with those.
One thing, Julius, that maybe didn't come up in the summary is that Muon actually is designed only for specific parameters in the parameter space. So it is not used for all layers. So things like the
Ah,
embedding, it's not used for that. You would use Atom for those independent ones.
mhm,
It's only going to be used for the ones where you're doing a dense network.
mhm. Also, does everybody
And it's,
go ahead?
well, also, if you go back to the previous slide, um, I'm not sure how it got to that equation normalized update. Um,
Yeah, I'm not
later,
sure if that
late,
equation's correct.
yeah, I'm feeling the same way. So I
Oh,
think
yeah,
if we go back to eventually we can come back to the paper,
yeah. Let's go
and see
back to
what
the
the
paper.
update is. Yeah,
Yeah.
yeah, yeah.
Yeah,
So,
and we talked about this a little bit before. We texted about. I did look at the paper. I did look at the update, and this is oversimplified. It's kind of okay in spirit, but yeah, it's oversimplified. In fact,
there might be some norm where that makes sense. But
yeah.
I'm having a hard time. It's not a norm. It's not a norm that I would know.
I just posted a image in the chat that's from the Muon article. Is that does that look like it is? Um,
Yeah, I was trying to find the
Well,
other
yeah,
log.
that is the one. Yeah, yeah.
Yeah, well, you
Right.
need Newton Schultz, right?
And Newton
So
Schultz, that Newton Schultz 5 is an approximation of UVT, where U and V are from a
Right.
SGD.
So, so just like before, um, where you had the Hessian decomposed into a product of three matrices, you can think of this as doing the singular value decomposition. And so the scaling, the normalization to the hypersphere happens after it's been rotated, not in its raw form.
Right.
And I think that's pretty important.
Yep. Yep. Because then it addresses the delta Y, the output, the impact on the output, and they talk about that as normalizing. So it's kind of all of in the SGD, no, sorry, SVD. Um, you have kind of the input direction, output directions, and a scaling in the middle. Is that rotate first, scale, and then rotate again? And they keep the rotations, but not the scaling, which is essentially, you could think of it as per dimension inverse of uh, this, what is it, the sigma? What's on the S is sigma, is that right?
sigma
On the
squared
Uh,
or
yeah,
SVD.
Yeah.
yeah.
So it's like you invert the sigma. That's the scaling per dimension.
Yeah. So if we reduce this to just two dimensions and you have an oval, an ellipse, that's that's diagonal. You can scale the x and the y directions, and it'll still be a diagonal ellipse. It'll never turn into a circle. If you rotate it to coordinate a line, and then you scale it, and then rotate it back, then you can get a true circle.
Right.
Cool.
And-
Well, I think we should go to the paper next. So I'll just finish up, okay? This is how much I had on Muon based on my search. And this is an AI summary of what I dug up. So let's get past this so we can look at the paper. So yeah, this is just high level summary. I think we
Mhm.
covered it. And this is Claude Opus wrapping it
Hey,
up.
Julius, we're
Yeah.
at time. How much
Ah,
longer do we have?
well, I'm
On
done. I
oh,
can just see I'm finished, and I have the summary matrix of everything. And so yeah, the only thing I would do next is go to the paper and we could all discuss the equations and figure out how to very precisely
well,
interpret.
there's always next week. We always like this.
I was going to ask that question. I don't know how. So I have some slides on Muon, and also I found a good talk that Bernstein, who did the theory of Muon,
Hmm.
um, that it's like a 47-minute talk, but his part talking about Muon specific, a bunch of its background, it was only like 15 minutes or something. It might be useful just actually watching that as well, depending on how long we want to stay on optimizers. This will be week 2, so I don't know if we want to go to week 3.
Yeah.
Maybe we want to go to week 3. One of the coolest things for me is that Muon looks at the fan in and fan out of a given node, which has been one of the things, the biggest kicks that I've been on since I read the Tensor Programs 4, Tensor Programs 5 papers like 2-3 years ago. And I guess it was just a little bit difficult to implement those, and so people didn't necessarily super widely adopt the maximal update thing from those papers. But Muon does a variation on that, which
they kind of just threw it in, right? It's independent of the update rule. They could have done it without it. They could have left that problem standing, but they didn't, and so yeah.
Okay. Well, it sounds like we have enough though to go further. Is that what I'm hearing?
I think if people are interested, I think we have enough.
Yeah.
Yeah.
And then this explains why also you need dense vectors, so you don't use this for embedding and unembedding matrices, even though those are two-dimensional. They are rectangular.
Yeah, maybe the way in which they use them. Bernstein's on this whole idea about redesigning optimization around specific norms, where the norm is per layer specific.
Yeah. Why don't we get some good ideas in for next week then to put this together? And
are you, Julius and Ted, are you going to both be here next week? Because I'm way over my head in the math, so I think a lot of discussion would be helpful.
I can try to be here. I'm not 100% sure. If I can't, then maybe we could postpone it, but it would be nice to keep it going.
Yeah,
okay.
I'll be around, although I don't know how much I can help you with the math.
It's scary for me, but it also seems like it's not like one path you can find to there's a lot of different competing ideas and perspectives, and then these darn AI agents that keep jumping into, you lean on them and then they send you off on some direction.
Well, there's a PhD thesis, I think, involved for someone to do on, does AI really help if you're doing PhD level research, or does it
there's like
does it take you down this little path?
Well, at least for software engineers, there's plenty of articles that say it does not speed you up at all.
Yeah. Well, you don't know. I think there's old guys that, like me, no gray hair, that want to stay in the old stuff.
Right.
And then there's new guys like you, Warren. Move ahead.
Yeah, it speeds me up. Ain't gonna speed anybody else up, but it speeds me up.
But it doesn't matter, right? As long as you're making money on the deal, that's good.
Yeah. Well, I haven't figured that part out, but
Yeah. Okay.
I'd say, somebody described this term, jagged intelligence, which I love the term, because these things can be smart in one area and stupid in another area, and it's a matter of learning. Like, how do I use this tool?
Yeah.
Jagged intelligence.
Well, that's a
if
good
you're not an
subject
expert in an area, it's good. It gets you up to speed for sure. And then you kind of have to bounce around between the models.
Yeah.
And I tell them to give me references, so I have them emphasize references. And when I have time, I actually check those references. And
that's tell them don't hallucinate. It works now.
Hey guys, since we moved off Muon, I'm going to stop the recording on this for that. Okay.
All right.
Okay.